Tia laser có thể rút ngắn thời gian xử lý chất thải hạt nhân từ 1 triệu năm xuống còn 30 phút. 1332. Đó là tuyên bố của ông Gerard Mourou, người đã đoạt giải Nobel cho công trình nghiên cứu xung laser nhanh. Cho dù người ta có nghĩ đến năng lượng hạt nhân với sức mạnh vượt trội như thế nào, thì điều không thể phủ nhận là việc tạo ra năng lượng hạt nhân đồng nghĩa xả ra hàng tấn chất thải phóng xạ, vô cùng độc hại mà người ta vẫn chưa biết làm cách nào để xử lý triệt để. Vì thế, nó thường được chôn giấu một cách an toàn nhất có thể trong các khu lưu trữ dưới lòng đất. Chất thải loại tồi tệ nhất, uranium 235 và plutonium 239, có chu kỳ bán giá là 24.000 năm. Đó cũng là vấn đề gây đau đầu cho các nhà chức trách ở châu Âu, nơi có nhiều quốc gia phụ thuộc vào năng lượng hạt nhân hơn bất kỳ nơi nào khác. Vì thế, khi nhà vật lý Gerard Mourou đề cập trong bài phát biểu nhận giải Nobel rằng laser có thể cắt giảm tuổi thọ của chất thải hạt nhân từ 1 triệu năm xuống còn 30 phút, những người quan tâm đến lĩnh vực chất thải hạt nhân đã rất vui mừng. Gerard Mourou cùng với Donald Strickland vừa đồng nhận giải Nobel cho sự phát triển của họ về chủ đề khuếch đại xung chớp CPA tại Đại học Rochester. Trong bài phát biểu của mình, ông đề cập đến niềm đam mê với loại ánh sáng cực mạnh. CPA tạo ra các xung quang siêu ngắn, cường độ cao, chứa một lượng công suất cực lớn. Mục tiêu của Mourou và Strickland là phát triển một phương tiện tạo ra các vết cắt có độ chính xác cao, hữu ích trong các cơ sở y tế và công nghiệp. Ngoài ra CPA cũng có một lợi ích khác, điều đó cũng quan trọng không kém. Các xung toxicon của nó nhanh đến mức chiếu sáng lên những bề mặt tạo ra phản ứng không thể quan sát được, chẳng hạn các quy trình diễn ra bên trong các nguyên tử riêng lẻ và trong các phản ứng hóa học. Khả năng này chính là những gì Mourou hy vọng, mang lại cho CPA cơ hội vô hiệu hóa chất thải hạt nhân. Mourou giải thích, lấy hạt nhân của một nguyên tử. Nó được tạo thành từ proton và neutron. Nếu chúng ta thêm hoặc bớt một neutron, nó sẽ thay đổi hoàn toàn mọi thứ. Nó không còn là nguyên tử như cũ nữa, và các đặc tính của nó sẽ hoàn toàn thay đổi. Tuổi thọ của chất thải hạt nhân về cơ bản đã thay đổi, và chúng ta có thể cắt giảm thời gian này từ 1 triệu năm xuống còn 30 phút. Chúng tôi đã có thể chiếu xạ một lượng lớn vật liệu trong một lần bằng tia laser công suất cao, vì vậy kỹ thuật này hoàn toàn có thể áp dụng được và về lý thuyết, không có gì ngăn cản chúng tôi mở rộng quy mô nó lên cấp độ công nghiệp. Đây là dự án mà tôi đang triển khai với sự hợp tác của Ủy ban Năng lượng Nguyên tử và Năng lượng Thay thế, hoặc CEA, ở Pháp. Chúng tôi nghĩ rằng trong 10 hoặc 15 năm nữa, chúng tôi sẽ có một cái gì đó mà chúng tôi có thể chứng minh. Đây là điều thực sự cho phép tôi mơ ước, nghĩ về tất cả các ứng dụng trong tương lai của phát minh của chúng tôi. Trong khi 15 năm có vẻ là một khoảng thời gian chờ đợi quá dài, nhưng so với việc đối phó với chu kỳ bán giá của chất thải hạt nhân thì thời gian này chỉ là trong nháy mắt. Tổ chức Hòa bình Xanh ước tính có khoảng 250.000 tấn chất thải hạt nhân ở 14 quốc gia trên thế giới. Mặc dù năng lượng hạt nhân đang đấu tranh để được chấp nhận là một nguồn năng lượng ở Mỹ sau một loạt các sự cố đáng lo ngại, cũng như sự xuất hiện của các nguồn thay thế như năng lượng mặt trời và năng lượng gió, nhiều quốc gia châu Âu đã chấp nhận nó. Pháp dựa vào năng lượng hạt nhân cho 71% nhu cầu năng lượng của mình. Ukraine là quốc gia phụ thuộc nhiều nhất với 56%, tiếp theo là Slovakia, sau đó là Bỉ, Hungary, Thụy Điển, Slovenia và Cộng hòa Séc. Không quốc gia nào trong số này có một kế hoạch tốt cho chất thải hạt nhân, ngoài việc lưu trữ nó ở đâu đó và hy vọng có một giải pháp cuối cùng. Hoặc để nó hàng ngàn năm và mong nó nằm yên, không thoát vào nguồn cung cấp nước hoặc không khí. Tổ chức Hòa bình Xanh ước tính có khoảng 250.000 tấn nó ở 14 quốc gia trên thế giới. Trong đó, khoảng 22.000 mét khối là nguy hiểm. Theo Hitachi, chi phí cất giữ tất cả là hơn 100 tỷ đô la Mỹ trừ Trung Quốc, Nga và Ấn Độ. Năng lượng hạt nhân có thể là ứng cử viên sáng giá nhất cho tương lai. Quá trình mà Mourou đang điều tra được gọi là sự biến đổi. Năng lượng hạt nhân có thể là ứng cử viên sáng giá nhất cho tương lai, nhưng chúng ta vẫn còn rất nhiều điều nguy hiểm đang rình rập khác. Ý tưởng ở đây là chuyển chất thải hạt nhân này thành các dạng nguyên tử mới không có vấn đề về phóng xạ, những gì bạn phải làm là thay đổi cấu tạo của hạt nhân. Mourou nói về kế hoạch của mình cho laser và lãng phí một cách rõ ràng hơn, nó giống như karate, bạn tạo ra một lực rất mạnh trong một khoảnh khắc rất ngắn. Ý tưởng về sự biến đổi này cũng không phải mới, nó đã được tìm hiểu trong 30 năm qua ở Anh, Bỉ, Đức, Nhật và Mỹ. Một số nỗ lực vẫn tiếp tục, một số đã bỏ cuộc. Rodney C. Ewing từ Stanford nói rằng, vật lý có thể hoạt động, nhưng việc chuyển hóa chất thải hạt nhân mức độ cao đặt ra một số thử thách, chẳng hạn tách các hạt nhân phóng xạ riêng lẻ, chế tạo các mục tiêu trên một khối lượng lớn quy mô, và cuối cùng là chiếu xạ và xử lý chúng. Mourou và Tajima hy vọng có thể thu hẹp khoảng cách một chùm ánh sáng phải truyền để biến đổi nguyên tử thêm 10.000 lần. Họ luôn nghĩ về điều đó, và cũng không xem nhẹ những khó khăn đang chờ phía trước.
Our next speaker is Professor Gérard Mourou, who's a French scientist and a pioneer in the field of laser physics. He was born in June 1944 in Albertville in the French Alps, a town probably best known for hosting the 1992 Winter Olympics, at least until now. Mourou started his career in physics at the University of Grenoble-Alpes, getting his diploma in 1967, and moving on to first Quebec and then Paris to work on his doctoral thesis. He received his doctorate from Pierre and Marie Curie University in Paris in 1973. Gérard Mourou spent a large part of his career in the United States, in particular at the Laboratory for Laser Energetics at the University of Rochester, New York, where one of his doctoral students, as we just heard, was Donna Strickland. Together, the pair devised the chirp pulse amplification technique, which today is at the core of most high-powered laser facilities in the world. In 1988, Mourou joined the University of Michigan in Ann Arbor, where he founded the Center for Ultra-Fast Optical Science. He returned to France in 2005 and became the director of the Laboratory of Applied Optics at the campus of École Polytechnique in Palaiseau, a post which he held until 2008. Mourou is a visionary, aiming to create lasers with unprecedented power. He initiated the multi-petawatt Apollon laser project in France and coordinates the large European extreme light infrastructure, ELI, that will host even more powerful lasers in Romania, Hungary, and the Czech Republic. He's currently also the field director of ICEST, the International Center for Zeta and Exawatt Science and Technology, established in France in 2011 to, among other things, develop the field of laser-based particle physics. Gérard Mourou has been the recipient of many prestigious prizes, but I dare say that this year's Nobel Prize must be the icing on the cake. With that, I'd like to invite Professor Mourou to join me on stage to give a talk staking out the future of high-intensity lasers. Professor Mourou.
Well, thank you very much for coming, friends, colleagues, former students, and so on. Well, it's always a dangerous act, to act up behind Donna, Anyway, I'm going to try, Donna. It's also a pleasure because there is many of my students in the audience. Students or co-worker, and for me it's very refreshing. It's like when we had our group meetings, at Rochester, at Michigan, and so on. Anyway, so I'm going to tell you. Can we blow this picture a little bit bigger? Yes. Okay, so I'm going really to talk about my passion about extreme light. So Donna gave you all the background, how to build these high-intensity lasers and so on. You don't need much more than that, okay? And but I'm going to tell you what you can do with that, okay? Because it's true that it's only recently that we had this phenomenal intensity available, and so there is many new discovery which are being made. Okay, so that's my passion for light. Okay, and do I have? Why does it work? Okay, I can maybe act. Okay, I can act here. So everything, like Donna said, everything and started with Ted Mayman, in 1960. I'm sorry, again. Yes. And there's one thing, which really strikes me about light is a variety of things you can do, okay? And as Ashkin, showed that what you can do, first thing is maybe you can slow down atoms. And it's a very, very interesting phenomenon we have seen with the tweezers and so on. And this, it doesn't work, it's okay. People, used it intensively, were very successfully, and trying to really use the light to decelerate atoms. And that led to the field of quantum optics and cold atoms. And you have Steve Chu in the first row here, which got the Nobel Prize with co-antanology, and also Bill Phillips. And so that led this fact that we can really slow down the atoms to very, very small times velocity. Very important. It's another way to say that it's a way also to make it atoms very cold and reach temperatures, which are, I think, the coldest temperature we can produce now. Okay, now the other thing you can do, and this is what is exciting, okay? You can do just the opposite. You can accelerate particles. And you can accelerate particles, like electrons, for instance, to the speed of light, or very close to the speed of light, okay? And this led, really, to a new field, which we call relativistic optics. I will tell you why we call relativistic optics in a minute. We know that light is relativistic, of course, per definition, almost. And so that, the fact that we can now accelerate particles to the speed of light, then led, of course, now to an enormous field, which deals with accelerator physics, nuclear physics, cosmology, nonlinear QED, general relativity, extra dimension physics, you name it. Very large physics. Okay, so I don't have to go to talk about CPA. We heard Donna saying it, of course, because we are going to need CPA, of course, to accelerate this particle and so on. So so CPA, we stretch the pulse, we amplify, we compress it, and finally, in order to get very short pulses. I like to say one thing, because it was a completely novel concept at the time, and because everybody, as you've seen, was into dye lasers, okay? Especially the guys at Bell Lab at that time. And here we came with Donna with solid state lasers. And so it didn't grab the attention of many people, except, I will say, a couple of one. One, for instance, was Suni Swanberg, who just visited my lab, because he had a hint that was something special. And also, I had the visit of people from Lawrence Livermore Laboratory, Mike Campbell, and so on. Mike is in the audience, because he, like me, they understood immediately that it was something important for power, increasing the power of lasers. Okay, so now with this CPA technique, what is fascinating is you can really produce very, very high peak power, and we are going to use this high power, I will show you in a minute. But just to give you a sense, the peak power, okay, of the light is in a now it's in a petawatt range, okay, which is about 1,000 times the total power of the worldwide grid, the global grid, okay. But of course, for femtoseconds, 10 minus 15 seconds. But nevertheless, it's extremely important. And if you take now this power, this petawatt power, and you focus it, like Donna said, over on a spot size, which is a wavelength of light. You cannot really go less than that, so typically a micrometers or so. Then you get a fabulous amount of energy density on a very small spot. And this, of course, is leading to absolutely new application. And just to give you an idea, okay, light, like the first speaker showed, and Art Ashin showed, and was fascinated by, really deliver pressures. But when you are talking about pressure light at a petawatt level, when you focus that on a small spot size, you can really produce pressures which correspond to about 10 million Eiffel Tower on the top of your finger. So it is the largest pressure that you can produce on Earth is with light, with photons. This is amazing. So now this is really the evolutions of intensity as a function of years. Okay, from the 1960, where Mayman invented the laser, and the first first 10 years, new technique improved the power and Q switching, more locking, and then the intensity plateaued. It plateaued because, like Donna said, you are damaging. If you go higher, you are damaging your laser inside. You damage. You're putting this nice big track, in your solid state amplifier, and of course makes your advisor very unhappy, right, Donna? And she learned the hard way. So anyway. So in order to prevent Donna making mistake, I said, well, that's not the way to do it. Let's do it this way. Okay, let's invent the CPA, okay? So she wouldn't really damage Ward anymore. Okay, so we did, she built it, and the CPA, and then we could really now, we are not limited by the breakdowns of material, and we could really climb up now the intensities. And now, since the 85, when we did it, the intensity, I have to say, has increased enormously. Okay, 8 or 9 orders of magnitude. Okay, and it's going to go further up. Okay, with lasers like Apollon that is being built, lasers which is part of the ELI infrastructures, Hungary and Romania and Prague and so on. So it's going up, and as we are going up, of course we are traversing new regimes of physics. So the first one, and Donna said it, we started to really observe multiphoton ionization differently and so on, and observe what she was saying. And so we climbed up as we climb up the intensity, then we go into relativistic optics. Why relativistic optics? Because for the first time, when you can see something, this means that you have electrons which are agitated, and because they are agitated, they are really producing light, which are coming and striking your eyes. Okay, so, but in a case of when you are passing 10 to the 18 watt per square centimeter or so, then what happens is now the electrons in your atoms move by a large amount and move at the speed of light. So the electrons, not the light, but the electrons are really moving at the speed of light. So So that's a very interesting regime, which leads to a lot of effect and so on. So now, of course, if you are pushing, this is what we are trying to do now. If you are pushing the intensity up, like we are trying to do with Apollon, Eli, and so on, then you go into the ultra-relativistic regime, and this time it is because not only the electrons can be moved at the speed of light, but also the protons which are massive, they are 2,000 times the mass of the electrons, so they are more massive, but at 10 to the 25 or so watt per square centimeter, they move at the speed of light, and that's going to be very important. Then finally, if we push even the intensity even higher, and I won't say exactly how we're going to do that. Jonathan Wheeler in the audience, and we can talk about it. But so we go into this regime where light interact with vacuum. Okay, like my friend Pissinchen says, we are boiling the vacuum. Okay, we are really separating the particles. Real particles and virtual particle in vacuum, and this is what we can do. And at this regime, which is 10 to the 28, 10 to the 29 watt per square centimeters. Okay, and basically what we do is we materialize the vacuum. Okay. Anyway, so moving right along. Okay. Again. So now there's one thing. If we go back to the regimes, at 10 to the 14 and so on, then we can really use these femtosecond lasers. So we don't add, for instance, to micro machines, to remove, to ablate material very, very precisely. The reason is femtosecond lasers are so good for that is because if you are using, for example, a continuous laser and you're shining the continuous laser on a target, then you are going finally to hit the whole volume of a target, so you cannot really micro machine with that. Now, if you are using pulses which are much shorter nanosecond pulses, which is, for us, is infinity, it's very long, but you do better because, of course, the heat doesn't have the time to propagate before the block is molten. And then you have the femtosecond laser where you come with a very, very short pulse and you deposit the energy and the temperature, the heat doesn't have the time to propagate, and you make these very nice holes. And it's a very, very precise way to really ablate the materials. And this gives you some idea, of what we could do, what we can do. In fact, very easily now it's really widely done everywhere. And you can see that we can really make holes and so on very precisely. There is no collateral damage, it's very clean. And very small, okay? You see that we have feature size, which is less than the micrometers, in size. And no damages. So, of course, now, one beautiful way to use this laser is to do eye surgery, because after all, eyes, is some biological tissue, and also is not the kind of things where you have to be accurate with eyes. And so we thought about that. In fact, we thought, because we had this little mishap happening in my lab, and this is one of my students who is in the audience. got a line in the laser, got a laser in his eyes. And immediately, we took the student, to the hospital, and they met ophthalmologist who is also here, Ron Kurtz, and so Ron Kurtz looked at Dieter eyes, both are here, and he said, "Wow, this is very strange." And yes, he got hit by the laser, but it's strange. And so Dieter said, "What is strange?" Well, it's strange because the damage on your retina is perfect. So that immediately, of course, we had the University of Michigan, excited about it. They put some money in it, and then that started the field of femtosecond laser, which is a very, very important field. Okay, so this is just to give you an idea what we can do, on the cornea. We can use it for all kind of things, we can in ophthalmology, and so it was very exciting. In fact, so if you are, I'm just show here, if you have a 50 picosecond laser, which is long for us, okay, or if you have 300 femtosecond, you can really create this flap, very, very nicely, and this is being done, now. There's also few ophthalmologists here in the audience, and it's great. So now I had a movie showing this creation of a flap. But I have to say that, and after some comments, people say, well, if you show this movie, maybe some people are not going to stand it, for it, because it's. So I'm not going to show it, okay? And I will save some time for busy. But anyway, if you want really to talk about that, here you have specialists. You have at least three specialists, on this thing here. Okay, now let's go back to my my roadmap here, and so as I said, so we were here for a short while, and now we are climbing up. As I said, we are in this area right now, and what's exciting here, when we are. Sorry, which slide is that? Yeah. When you are in this area of 10 to the 20 and 25, etc., when you are shining the laser over a very small size, I mean spot size, like Donna said, wavelength of light, then you are producing these humongous intensities, and you are producing particles, of any kind of particles, any kind of radiations with very large energy, okay? Very freely, okay? It's amazing. And so this is we call a universal source of high energy particle and radiations. And this type of course, of work is being done at Lund, not very well, in Sweden anyway. And if you are interested, there are people here. Okay, so now what we want to do now is we are producing. This was an idea from Tajima and Dawson. Toshi Tajima is a very good friend of mine, of a lot of people also. And he had this idea in 1979. He said, well, looking at ducks or whatever on the lake, looking at surfer and so on, he said, well, maybe we should use the same effect that is being used by surfer in order really to get particles moving. So they really wrote this very nice paper, But of course, it's 1979. So it's before 1985. So I didn't know about this effect, and Toshi didn't know about the CPA, okay? So, but fortunately, we had scientists at NRL, Naval Research Lab, who really were able to saw the potential to put the two concepts, CPA and laser wake field accelerations, together in order to accelerate particles. And this is what is going on now in the many, many laboratories in the world. You have lasers here, and you shine the laser on this gas jet, and you're producing a plasma, which is plasma is a kind of a soup of electrons and protons and so on. And you are creating this wave, these plasma waves, where the electrons are going to be trapped and dragged at the speed of light, by this wave. Okay, so this now, it is really, we were talking last night with Olga, this is really the future for electron accelerations. And because they have problems in high energy physics. They have problems because they have to build these huge accelerators. Here you have the CERN accelerator, the LHC, 27 kilometers in circumference here, and 170 meters underground. So it's really, of course, it costs enormous amount of money. And now, because for the next step, the next collider is going to be even bigger, okay, and will cost really an affordable amount of money. So really, it is very important really to come and with the new technology. And you think that if you're really replacing the technology used right now in this case, for instance, which is we're using radio frequency, microwave, and so on, where you have the gradients is of the order of less than 100 meters, 100 MeV per meters. That's the reason why you have 27 kilometers. But if you now are using this novel technique, the Tajima's idea to accelerate particles, then you could really fit, a CERN, in principle, okay, a CERN on a football field, okay. So this is pretty good, okay. But of course, we like with Toshi to look ahead all the time. And so some people, in the agencies have difficulty to see that, but anyway, this is the way we are, okay? And so we like to look ahead. And so right now, let me tell you that we can produce now something like devices, GeV devices, are centimeter size. Okay, now we can produce up to 5 GeVs, but 5 GeVs is something like 10 centimeters in length. Okay, and yes, we could really maybe put CERN on the football field, but could we do much better than that? And right now, and the reason is yes, we could, in fact. And I'm not pulling your leg here, okay? We could already, in fact, make the accelerator kind of TeV accelerator on a fingertip. And by doing what? Okay, instead of using gas, which has a very low density of electrons, then we would like to use solid. Solid, and so you have 6 orders of magnitude larger amount of electrons, okay, because we are working also with gas at low density gas. And then, but you say, wow, but I mean now light won't be able to propagate through the solid at this very high intensity. And so we say, okay, fine, but if we can really develop a high intensity X-ray now, so that is, instead of working in the visible, work in the X-ray regime, then with the X-rays, high intensity can penetrate into the solid and to produce this wake field. This is exactly what we are doing right now, you know, at the École Polytechnique, and in collaboration with, of course, with Toshida Jima at Irvine, and also with some people from the Eli, okay? Because we think really this is really maybe the future, trying to work with laser wake field accelerations in the high energy X-ray regime. So we have ways to do that. I don't have the time to show it, but it's really, I think there is really new avenue to do that. Now, yeah, I just a quick reminder that there is this three phenomenal facilities which are being built by the European Union and which are really in Czech Republic, in Hungary, and in Romania, where you have absolutely three beautiful facilities were really doing different things. They don't do three times the same thing, of course. And and it's absolutely fabulous to have in few years, you know, we will have them working and welcoming large amount of users. And so Eli, for instance, is very close to get to the 10 petawatt objective. Now, you know, what is there's a big application coming back to societal applications. There's a very important applications if you can produce beams of particles. Let's suppose that you can really produce beams of protons. Well, you know, protons therapy, for example, for cancer and so on, is really the therapy of choice. Okay, because the protons, not like other radiation of particles, they don't burn the tissue between really the skin and the tumors. You can really address the tumors almost, you know, uniquely, so you can deposit your proton exactly in a tumor. Now, also, what is nice about having these high-intensity lasers is you can make particles, and these particles, you know, can be radionuclides and so on, and you can use them, you know, to implant these particles into the near the tumor or in the tumor of the patient. Also, you can use these radioisotopes and so on, but you know, which in order to do all kind of diagnostics and so on. So this CPA, high intensity or extreme light intensity or lasers, you know, are really very useful, but will be very useful in the medical world. Now, there's also another applications, but this is dreaming. But I like to dream anyway, so I did that all my life and made my living with that. And so anyway, so there's one really big problem we have. And this also, together with Toshi, we're working on it. And by the way, we're not working because it's easy. We are working on it because it's difficult. Okay? And what we want really to do is to transmute nuclear waste, because we have all nuclear energy is maybe the best candidate for the future, but you're still left with a lot of this junk, dangerous junk, and that's the reason Toshi invented the terms now. Toilet science. It's time to do toilet science. It's time to clean up what we have produced, producing energy and so on for our living. And so the idea now, of course, is we have to find ways, okay, to mitigate, this nuclear waste. And one way will be maybe to transmute this nuclear waste into a new form of atoms which are not which don't have this problem of radioactivity. And so what you have to do is to change the making of the nucleus. Okay, so for example, if you have a nucleus atoms A, okay, and you have a isotope A, and which is maybe radioactive for a long time. So like take the example of technetium, for instance, and which can be radioactive for 100,000 of years. Then if you can really lodge a neutrons, because now we have freedom. We know that we can produce any kind of particles, including neutrons. We can produce neutrons, in this in the nucleus. Then you are changing the isotope A into an isotope B. But this time, it can have really now radioactivity time release of the order of seconds. Of course, this is the most favorable case. But so we would like to extend the concept, to, of course, the nuclear waste, which are really polluting our life right now. So by the way, sometimes you're lucky, and this isotope B becomes isotope C, and it's stable, so it doesn't emit anything. So, in conclusion, for me, is extreme light is capable of generating the largest fields, the largest accelerations, the largest temperature, and the largest pressure. Just with light, it's amazing. And it carries the best hope and opportunity for the future of science and technology. So, thank you very much. And I would like to add that we are doing this. It's a very rich field right now, the field of extreme light. But I think the best is yet to come. Thank you very much.
So this concludes the physics lectures for this year's Nobel Prize 2018. I would like to extend my profound thanks again to our three eminent speakers, Dr. Essiambre, Dr. Donna Strickland, and Dr. Moreau, for wonderful talks. And having said that, I would finally like to invite our Nobel laureates, Donna Strickland and Gérard Moreau, to come up on stage with me so that you may congratulate them again to this year's prize. So please.